Right. If you recall, in the last session, we learned about reduction of acids and derivatives. That was the last thing we learned, in which we saw that if we have to convert carboxylic acid into alcohols, uh, we can't simply use catalytic reduction. Instead, we need to change the catalytic to an highly activated form, and that would be used as a reducing agent. NaBH4, on the other hand, can only make an acid-base reaction, while lithium aluminum hydride can first give acid base and then continue all the way up to alcohols. And I discussed how the mechanism works, and you notice that the ratio at which the carboxylic acid and lithium aluminum hydride reacts is approximately 4 is to 3. This is the minimum ratio that is required for it. Okay. Next, the next reagent which is extremely favoring the acids is diborane. Okay, diborane is one of the strongest reducing agent, especially for acids. Extremely reactive, extremely towards reactive towards COOH and reduce COOH selectively in presence of other groups. In presence of other groups. So which means it will give carboxylic acid as the priority. So how does the reaction go? So like this, carboxylic acid, and if you react that with first B2H6 and THF, and then treat this with H3O plus. One second. Okay. So that will convert into an alcohol form, RCH2OH. Got it? What does that selectivity means here is if you have a COOH here, and then I treat this with one first B2H6 and THF followed by hydrolysis, correct? And imagine I take only one equivalent here, right? So in that case, you will see that this CH2OH will get reduced. Double bond is not going to get reduced. So selectivity wise, if you compare, the selective reduction of acids is way more favorable than alkenes, then alkynes, and then comes aldehydes and ketones. So it is highly responsive towards uh, acids as compared to that of aldehydes and ketones. Okay, mechanism is little complex, but I'll just give you a hint about it, because again, students would usually keep on asking like, sir, eventually what happened in the mechanism and so on, why this change has been occurred, and so it's better that I'll give you basic idea how it goes through. Okay, so notice this one. Suppose if you have an acid like this, double bond O, and BH3 is in close vicinity to this lone pair. So we know that this pi bond would attack on boron here because it's making more of a Lewis acid connect. So you will have O with BH2 and H with plus and minus, and here we have OH. Okay, here we have OH. Now notice this OH here, this H minus will take this H plus, and this double bond will shift here, and then this bond will shift onto oxygen, and that will make it O with BH2, and here I'll get double bond O plus H2. Okay, This is the first thing that will form. And this intermediate which is formed will again react with the second mole of BH3 lone pair trying to connect from here, and that would give us oxygen connected with BH3 with plus and minus here. Got it. And if you notice, this BH3 connect here will have BH2 with here bond like this. And what you can expect is that this H minus will attack here and this bond will go here. So that would make it to connect to formation of OBH2 and OBH2 with H getting added onto this position. Okay. And now the lone pair of this oxygen will try to connect back on the boron here. Okay. You will see some kind of a four-member ring formation observed here like this with oxygen and boron, and this oxygen and boron having BH2 with plus, and here we have BH2 with minus. Okay. So of course, boron having negative charge is an advantage this oxygen. So oxygen will try to break a bond, bring it back into a double bond, and this bond will break. Got it? This bond will break. Clear? Sorry. First, I'll not break this bond. Sorry. The lone pair. The lone pair on oxygen will push the bond here, and this bond will break. And as this bond pushes here, I will get this as uh, double bond O with BH2 minus connected with OBH2 this way. This is what it will have. Okay, clear? And now this is where the hydrogen is right now. Uh, so again, internally you would notice that this boron also has a hydride which can be given here. So this H minus will be given, and that will convert this into O minus. Okay, so making that into O with BH and OBH2, and these two are the hydrogens which have already established. And here onwards, if you make hydrolysis, so you can clearly notice that this form will become an alcohol like this, and here we will have 1 mole of BH3 will be out, 1 mole of boron will convert into boric acid. So in short, if you notice, we started with 2 moles of BH3 here, here and here. These are the 2 moles of BH3 that we used. Okay. And that has been finally converted into uh, primary alcohol, and 1 BH3 is out here. Clear? So it is almost like a 1:1 ratio. So if I write the overall reaction, that has to be RCOOH plus BH3 on hydrolysis. Got it? That is giving RCH2OH plus BOH thrice plus H2 plus H2. Okay, this is what you will get. Again, like I said, this is not a very favorable mechanism that you need to remember. This is only for your understanding, like in case we have an acid, how the reduction takes place. What is the takeout from this reaction here is this. See, acid chlorides, esters, right? Esters or anhydrides, RC double bond O, OC double bond O, R dash. These, when you react with B2H6, right, and hydrolysis, this will not make any BH3 reaction. And that can be explained in two ways. That you can see there has to have a hydrogen so that first an H2 can come out, and then the oxygen should connect internally, and that is only possible when you have it with acids. That's the reason why B2H6 is extremely reactive with carboxylic acid. See, other way, I mean, many other books explain with this particular fact that instead of just thinking in this term of a particular type of mechanism, there are many ways of mechanism. The earlier, the one which I gave you, one of the kind. What has been noticed is that RCOOH, when you react with B2H6, correct? Of course, one mole of H2 will be out, but the other mole, I mean, the boron would be actually connected as an intermediate like this with 3 moles of it. This is another part of explanation which was been given, and the lone pair of this would always be strongly resonance stabilized with boron, and that keeps this triacyl triacyl borate more stable, more stable form. Okay, so because of this acyl borate form, this reaction is more probably happening better for acids. Now you might think, what about esters? Can't we do the same thing with esters? See, when it comes to esters and then you have BH3, this attack is weaker because this will be resonance stabilized. Unlike in acids, you can think like C double bond O minus is formed after H plus is gone. So the attack of this O minus is relatively better. This is weaker. That's why esters does not make that impact on BH3, while acids will make that impact on BH3. Okay. So remember why it is not very favorable conditions for these cases, right? Is because this type of triacyl borate ester formation, which is very stable, is not observed. Clear with this idea? This is with B2H6, everybody. Done? Right. Now let's see what are the other reagents which will help in acids to get reduced. Correct. If you take dival H, dival H, acids with dival H, dival H will only make an acid base reaction, RCO minus plus H2, correct? And you'll have this as dibal minus, dibal minus. That's it. Okay. Sorry, dibal plus. So here, but you will not see further reaction happening. So acids are not very good for reduction here. Instead, what are the acid derivatives here? That is esters, C double bond O O R dash. That when you react with dival H, first it will convert into an aldehyde form like this with R dash O minus, and then on if you hydrolyze this directly here, correct? Sorry, then again it can react with dival H, and that can convert into an alcohol, that is RCH2OH and RCH2O minus, RCH2O minus and R dash O minus, and that on hydrolysis will convert this into alcohols. So which means esters can be reduced, but this is the tricky part, everybody. In JE questions, if the dival H is given, right, he's assuming the default temperature as minus 78 degrees. Okay, so let me put this as a note. In JE questions, okay, dibal H is by default by default dival H at minus 78 degrees Celsius. In that case, in that case, so dival H, this by default dival H at minus 78. In that case, okay, esters only reduce up to aldehydes and no further reduction. It will not go for further reduction, which means if you are expecting that aldehyde is expected to convert into an alcohol, correct, with dival H, in that case, temperature must be given. Otherwise, if it is only given as dival H at minus 78 degrees or nothing is given, that means you will not consider it to further reduce. This is very important about dival H information, everybody. And now notice, if you have acid chlorides also, acid chlorides, dival H will react, dival H will react and it will convert into an aldehyde. And if you have cyanides also, dival H will react, convert into an aldehyde. Okay. With amides, only acid-base reaction will happen, RCONH minus and di dival plus H2. That's it. So no aldehyde or keto formation here observed. So these are the derivatives. So you can see whether it is, by the way, anhydrides and esters will have very similar reactions. So anhydride, how it is been done, esters, how it is been done, the same thing happens with anhydrides. Okay. So I want you to make sure that you are very clear about dival H, everybody. Okay. So dival H, in fact, does reduce all of them. Okay. Except for acids and amides. But they all to be reduced only up to aldehydes. Clear? I guess this part is done. Next. The next reagent which can be used for reduction of acids is dissolved metals. Dissolved metals, in which one which is most used is sodium in ethanol, known as Bovolt blank reduction. Bovolt blank reduction. Okay. And with RCO minus with sodium and ethanol, this will convert into RCH2OH. Here there is no temperature condition. Even aldehydes will all convert into alcohols only. Everything will convert into alcohols. Mechanism wise, if you notice, we have R, C, double bond O, O, R dash. Electrons are released by sodium, which try to connect onto carbon, getting this as O minus single electron and OR. Okay. Now, one more electron will be pushed here till it becomes carbanion. So you'll get this as O minus, C minus, and OR, which will be reacted with the ethanol to take H plus, and that's how you will get this as R, C, O minus, CH, and OR. And this O minus will push here to remove this OR, thus converting that into an aldehyde form. And we already learned the aldehyde reactions earlier in the mechanism also, that aldehydes in the presence of sodium and ethanol, if you continue to do that, it will convert into an alcohol form. So that's why almost almost sodium and ethanol, that is Bovold blank reduction, happens with all other reagents as well. Got it? So which means if you take acid chlorides, or you take anhydrides, or COC double bond O, OR dash, okay, that as you react with sodium and ethanol, it will give you alcohol directly, RCH2OH, or RCH2OH here, plus R dash CH2OH. Correct? This is the type of reaction that happens with sodium and ethanol. Well, does it make any reaction with acids? See, if you have RCOOH and RCONH2, if you react with sodium and ethanol, correct? Here also it makes a reaction, converts into alcohol and amines. Okay, but poor yield. This will be poor yield, right? So this is not usually reported that easily. So this reaction is not reported that easily because the reaction is not very strong. Got it? So it is not very prominent for acids and amides, but for acid chlorides, anhydrides, esters, this can be very well used. Got it? Next. This is all about esters, everybody. Okay. Then we'll see reduction of acid chlorides. Reaction of acid chlorides. Now, there are two types of reductions that happen here. If I take acid chloride and react with, H2 in the presence of palladium barium sulfate or calcium carbonate, then it will convert into aldehyde. Okay, one second. It will get to an aldehyde form, and further there is no more reduction. H2 and palladium barium sulfate does not make any further reduction. Okay, but if you have acid chloride reacted with, H2 in the presence of only palladium, first you will get aldehyde, and that will further reduce to convert into alcohols. So acid chlorides will be pretty much reductive, all the way towards alcohols in this case. Got it? And now, if you have acid chlorides reacting with lithium aluminum hydride or even sodium boron hydride, in both cases, it will convert into an alcohol form. I mean, it will go all the way up to aldehyde and then convert it to alcohol. And acid chlorides are also very well reactive with, sodium in ethanol, which I just told you. So that will convert into RCH2OH. Got it? So these are all the reagents that can be used. Got it? Dival H, I have already informed you that RC double bond OCl. If we use Dival H, it will only end up at aldehydes unless the temperature is specified greater than that of this temperature. Hmm? So that means at room temperature, it can go all the way to alcohols, but otherwise aldehydes. So these are the conditions for uh, acid chlorides. Got it? Now let's see few examples to examine, I mean, which case what to do. Got it? So let's notice these examples, everybody. So first example, see, in case if you have some kind of cyclic anhydride. Cyclic anhydride, when you react with lithium aluminum hydride, it will reduce all the parts. That means it will convert into an alcohol here and it will convert into an alcohol here. While if you react this with sodium boron hydride, actually sodium boron hydride reduces on cyclic anhydrides only, not in regular anhydrides. So it will become CO minus, and this side it will become an alcohol, correct? And this alcoholic part will be again connected to acid, convert into on hydrolysis, because sorry, not hydrolysis, with ethanol. Here we have. So it will compete to again get back into the formation of uh, ester formation now. So ester is what you will report as the final product, cyclic ester. So see the difference in the product here. So this is the difference in the product here. Second example, suppose if you have like this, we have acid on one end and ester on one end, correct? And acid chloride on one end. Okay. So these three are reacted first with lithium aluminum hydride, H2 by Pt, H2 by palladium, barium sulfate, okay, and then NaBH4. Then we have only dibal H, and lastly, I'll write down this side. Lastly, we have B2H6. Okay, sorry, one more is there, which is sodium in ethanol. Okay, these are the reagents which we learned, and you should be comfortable in all of these reagents. So check out first one. We'll see we will have this getting reduced, this side also getting reduced, correct? This side also it is getting reduced, and ethanol is also forming. So all of this would happen. And when it comes to H2 and PT here, correct, you would notice that only neither the acids nor the esters are easily reducing by H2PT. Got it? H2PT will not help in this reduction. Right. So what do we get here? So this acid chloride definitely get reduced. That's it. H2 by palladium barium sulfate, you know that it would be even worse. It can only reduce acid derivate acid chlorides into uh, aldehyde form. Rest will remain the same. Next, with NaBH4 also it is the same thing, but here you will get alcohol. This acid will remain the same, and this ester will remain the same. Correct? Dibal H. In case of dibal H, this will also become aldehyde. Acid will remain the same, and ester will also become aldehyde. Right? This is a product. With B2H6, B2H6 is extremely reactive only for acids. So acid chloride remains the same. COET remains the same. Sodium in ethanol, it will hardly reduce acids to a larger extent. So that's why I'm not taking acids into the account here. You'll get an alcohol here. You'll get an alcohol here plus ETOH. That's it. These are all the products that you will notice. All right. So please go through it quickly. Check out what are all the reagents and with acid chlorides and this. Okay. Take it a minute's time and see if you are able to, understand all the reagents. What are their restrictions and what is their selectivity. See this question now. What if you have a ketone on one end and NO2 on the other end? And then you are treating this with, you know, treating this with NaBH4, NaBH4 and lithium aluminum hydride. Okay. So keep solving it, everybody. Next. Third one. Third one. Check out. What if you have like this? This is an aromatic ring. You'll have C double bond O. Sorry, you'll have methyl here with COOAT here, correct? And COCl here. In that, if you react with lithium aluminum hydride, and on the other hand we have sodium boron hydride. Next, what if we have cyclic amides NH like this with lithium aluminum hydride LAH. Next we have sodium boron hydride SBH. Then we have H2 by PT, and then we have dival H, right? So let's do these three questions first. So first thing you will notice is NaBH4 will definitely help convert aldehydes, ketones into alcohols, but it does not interact with NO2. While lithium aluminum hydride even reduces NO2 to NH2. So that's the difference you need to identify between these two. Second, here this aromatic ring is not going to change, but here certainly you will get alcohols and alcohol. With NaBH4, you will get an alcohol here, but the other part does not changes. That will remain ester. Next here, lithium aluminum hydride will help in converting this into, sorry, converting this into secondary cyclic amine, while NaBH4 does not make any reaction. H2 NH2 will also make the similar reaction. Dival H again does not make any reaction. Okay, these are type of reactions you will check. Next, in case, sorry, it's not a question, so put it as a note here that if you have to figure out the number of moles of each cases, right? So you'll see 4 moles of aldehyde plus 1 mole of lithium aluminum hydride is sufficient enough to convert into 4 moles of alcohols, 4 moles of RCH2OH, while 4 moles of ketone will also be sufficient enough with 1 mole of lithium aluminum hydride to convert into R, CHOH, and R. And then if you notice the acids, it is RCOOH plus 3 moles. This is what we learned already. 3 moles of lithium aluminum hydride will convert into 4 moles of alcohols, and 1 mole of H2 or 4 moles of H2 will also come into picture, right? Next, if you take 2 moles of RCONH2, that is enough for 1 mole of lithium aluminum hydride to convert this into amines. So you'll get 2 moles of RCH2NH2, right? So this is the mole ratio that you need to remember for lithium aluminum hydride. Got it? Let me give you some JE questions which have recently been asked. Check out. This is from JE 2026. Recently asked COET and COOH. If it was given with lithium boron hydride followed by hydrolysis, or can have, okay, BH3 followed by hydrolysis. Then what do we get? Now listen up. Lithium boron hydrate is specifically designed to convert esters into alcohols. Okay. That has no role whatsoever with acids. So acid would remain the same like this, and this will convert into an alcohol. Okay. While the reverse will happen with BH3. BH3 is specifically designed to get no reaction with esters but make a reduction of alcohols, acids, sorry. So this is a product that you will get. Okay. So keep this in mind. What is the difference between BH3 also? Correct. I suppose these questions are clear, everybody. Please go through it once quickly. Check out this third, fourth. Uh, okay, I'll write it as third only here. So third, fourth, and fifth. Please check. See, with organometallic compounds, specifically when you react with O2, RMGX is used. So with O2, you'll get this as ROOO minus and MgX plus. And that when you react with, you know, RMgX, so that will convert into RO minus MgX plus of 2 moles. That on hydrolysis will give you 2 moles of alcohol. So this is typical way of preparing it. In fact, RMgX, if you react with aldehydes, various aldehydes, you know that followed by hydrolysis, so HCHO, followed by hydrolysis, we will get RCH2OH, primary alcohol. If you react with first CH3CHO, then followed by hydrolysis, will give you RCHOH and CH3, 2-degree alcohol. And if it is with regular ketone like acetone, okay, like acetone, like CH3CO, CH3, followed by hydrolysis. That will give you tertiary alcohols, OH, CH3, and R. So this is the product you will get. Got it? See one typical example. If you have an aldehyde present here like this, and then there is a bromine here, that on reaction with magnesium and ether will convert this form to MgBr, and double bond OH is present. That minus will connect, right? So MgBr is there. So this minus which is forming will connect onto this carbon to make an addition reaction there. And that's how you will get an alcohol. So you'll get a 4-membered ring, correct, with an alcohol form on hydrolysis. Okay. What if you use acids or acid derivatives on Grignard's reagent? Acid, when you react with RMGX, so basically you'll get, this is R dash H and RCO minus MgX plus. Problem here is magnesium does not polarize O- so strongly that the second mole of RMGX could attack. Okay, let me put this as a note. Magnesium MgX plus cannot strongly polarize like lithium plus to increase the delta positive charge of C double bond O minus group. Okay. Hence, no further reaction will take place. Hence, you will see no further reaction. Okay. So, especially Grignard's reagent will only stop at acids and base if you are reacting with carboxylic acids. Okay. While if you take acid chlorides esters, we know the mechanism already. If you have acid chlorides or if you take esters, right? And that when you react with Grignard's reagent, like R dash, let me take an example of CH3 just to make sure that we don't confuse with these R groups. CH3 MgBr followed by hydrolysis. In that case, you'll get an tertiary alcohol. So we'll get OH, CH3, CH3. And another alcohol which you will get is this one. This is the one which you will get. Okay. Same goes with anhydrate. So we don't have to rewrite again and again. Clear? If it comes to amides, again very interesting. In case of amides, if you react with CH3 MgBr or further any Grignard's reagent, you will get acid-base reaction and further reaction is subsided. So O minus MgBr plus and CH4. And if you have further moles of CH3 MgBr, no such reaction will take place. While in case if you have RC double bond O NR2, since there is no hydrogen, no acid base reaction, this time the reaction will happen CH3 MgBr of 2 moles followed by hydrolysis will give you tertiary alcohols as the above reagents. So we'll get CH3, CH3 and NH4 plus and magnesium will become Mg, Br and OH. Okay. So this is a type of product formation you will notice from acid derivatives. This is from Grignard's reagent. Another reaction from Grignard's reagent where you can get alcohols is when you have epoxides. And you know that epoxides are extremely conditional. If you have any substituted methyl here, then CH3MgBr strictly rely on SN2 mechanism. So which means the CH3 minus will attack on the less substituted side, open the bond up, and you will end up getting this as sorry, O minus MgBr plus, and that on hydrolysis, final hydrolysis, you will get this as alcohol, right? This is the product formation. Got it? Now, few important factors of RMJs that we need to know is that in case if you have an isolated double bond here like this, double bond O and double bond here, and then you treat with CH3MgBr in excess also, still the double bond does not get affected. The double bond is not reactive with this case OH, and this will form O minus MgBr plus, and that on simple hydrolysis will give you alcohol. Okay. Now, even if you have conjugated form like this, if you have a conjugated form, so now I'm pushing the double bond to the other position with CH3MgBr excess, still you will end up getting the same type of product. MgBr here, while double bond which was here in a conjugated form, and that after hydrolysis also you will end up getting same type of product here, which is OH like this. But here is the difference. Instead of alkyl, if you have aryl, correct? Instead of alkyl, imagine if you have aryl. That means if you have PHMgBr, PHMgBr. Now PHMgBr does not give this type of addition where directly it is attacking here. PHBr will attack on this position and then push this double bond here. So that will make more of, the first case was making more of 1,2 addition. This is called 1,2 addition product. While here you would notice 1,4 addition is more favorable. That means double bond will be shifted here, O minus will be here, and pH will be forming here, and MgBr plus. So what happened here now? It has got 1,4 addition reaction. So 1,4 addition has happened. And after that, if you hydrolyze it, you will get back to the keto formation here, pH, and this will become OH, and that OH will undergo tautomerism to convert back into ketone like this, pH. Okay. Now for this, do we require any assistance of water? Not so much. Even this without water also it can make it tautomerize. Without water also it can get tautomerized like this, and you will have keto form here with pH here. And that means if you react with the second mole CH3 MgBr, this time it will make 1,2 addition. So O minus MgBr plus, sorry, not CH3, pH. pH MgBr. Now pH will come here. One pH was already there. And now when you do hydrolysis, it will convert into an alcohol form. Correct? So what have you noticed? First is 1,4 addition. Second one is 1,2 addition. So this is 1,2 addition. So 1,4 addition is followed by 1,2 addition if you have a conjugated system. In which case, only when you have pH MgBr. Now, instead of pH MgBr, now I'm taking a case, right? A similar case here with alkyl, but instead I'm taking this as CuX, some copper salts. The minute you make copper salt, note what would happen. See, the minute we take copper salts here, CH3 MgBr will start connecting as a ligand with copper, right? Plus here with X minus here and MgBx2 here like this. This kind of formation you will notice. So you would start getting, a positive, a copper complexated compound, and this will reduce the nucleophilic nature of CH3. And in such cases, again, 1,4 addition will take place. So which means you will be adding CH3 here this time, pushing the double bond O minus MgBr plus. Correct? And that when you react with the second mole, only when you react with the second mole, that's when again 1,2 reaction will take place. So you'll get CH3 here with O minus MgBr plus. And that on further reduction with water will convert into an alcohol form. CH3, CH3 and OH everybody. Okay. So I want you to specifically check this out carefully in case if you have any cuprous salts along with Grignard's reagent, what is the final product? Okay. It will be always 1,4 followed by 1,2. So you can say this is 1,4 addition followed by 1,2 addition and then hydrolysis. Please notice quickly everybody. Now you might ask, sir, why this is happening? So let me put this as a note. 1,4 addition is favorable if nucleophilic strength is weaker. So, which is copper is making it weaker. If you have phenyl with CM3 MgBr, that will also make it weaker. That's the reason why you will get this as 1,4 addition more often. All right, so please check it out quickly. If you have any doubts, you can ask me, but please check this out carefully. What happens with 1,2 addition, 1,4 addition? Okay. In case of epoxides, in case of epoxides, right? Suppose if you have like this, and I'm expecting this to convert into an alcohol here like this, 1, 2, and then 1 comma 2, and then sorry, CH3 this way. So either I would get, sorry, first I'll write on this one, alcohols. This kind of an open alcohols here. So I want to get this H minus to be added. Then which are the best reactants here? So here H2 by PT, nickel, palladium, all of them will be good. Okay. Sorry. This will not react. And SBH, it is NaBH4. NaBH4 will not react. And LiBH4 will also not react for it. LiAlH4 will make a lot of impact. Dibal H, okay, at room temperature, that will make an impact. Sodium in ethanol. Sodium in ethanol is a good reducing agent. B2H6 can also impact this. So these are the only reducing agents which can convert into this open chain. Okay. I suppose this is clear, everyone. Right. So whatever we have studied so far, everybody, these are all the preparations of alcohols. Okay. Now let me take you through the chemical reactions of alcohols. Chemical reactions of alcohols. In chemical reactions, see, when it comes to alcohol, there are two types of bonds which it has. Okay. One is, reaction involving this bond, CO bond breakage, CO bond breaking reactions, or then we have this bond breaking, which is here OH bond cleavage reactions. Got it? These are the two types of reactions that you will notice. So first we'll see, right? The first category we'll see is OH bond cleavage. OH bond cleavage reaction. Out of that, the first one is sodium metal, also known as the sodium metal test. So alcohol, when you react with sodium in the presence of uh, ethers here, so that will convert into RO minus and Na plus half H2. So in a way, this becomes a source for making H2. Next, if you have similar type, sodium, right, alternative, magnesium, aluminum, and potassium can also be used. Okay. Next, once you get this RO minus, it would become an important reagent for a uh, very strong, very standard reaction known as Williamson ether synthesis. Williamson ether synthesis. Since we have already learned this in alkyl halides, if you could just recall that, what might be the reaction? Let me show you. RO minus Na plus, so which is the reagent we just created, that plus any R dash X, as long as this R dash X is SN2 ready reaction, then we shall get this as ROR dash. So ethers. So ethers are being prepared by this. Got it? Another alternative reactions here, alternative reactions include alcohol directly reacting with dimethyl sulfate in the presence of OH minus. Got it? So that will also convert into ROCH3 of 2 moles plus SO4 2 minus. Mechanism wise, if you notice, we have ROH in the presence of OH minus to convert into uh, to give this into RO minus plus H2O. And now this RO minus, as it reacts with methyl, which is connected with sulfate. So in fact, RO minus of 2 moles can be utilized. 1 mole attacking here, O minus is relieving. Attacking here, O minus is relieving. Right? So this way, you will get 2 moles of 2 moles of ROCH3 and a sulfate formation. So that's how you can get this product formation. Second reaction where this RO minus is useful, correct? So where we can use this alcohol form is that you don't even need a base alcohol when you directly use with diazomethane. Diazomethane. Here also you will end up getting this as ROCH3 plus N2. Now is the mechanism going on here. So ROH plus, structurally diazomethane is like this, CH2 minus and N2 plus. And this CH2 minus will take H plus from here, resulting that into RO minus and CH3 N2 plus. And N2 plus is an excellent leaving group. So RO minus will back attack on it via SN2 mechanism here, right? And that will give us ROCH3 plus N2. So this way you can get ethers. In fact, while reading ethers, you don't need to again keep revising all these reactions, because these all becomes the preparation reactions for ethers, everybody. These are all the preparation reactions for ethers. Got it? Next, alcohols, in case if you take 2 moles of it and use it with concentrated H2SO4, correct? At around 413 kelvins, then you will end up getting an ether plus H2O. It's a very important temperature condition. Okay, 140 degrees Celsius is 1413 kelvins here. So basically, you will get ROH plus H plus, which is coming from concentrated H2SO4. The first mole will connect onto H plus, converting that into ROH2 plus. Okay. And the second mole of alcohol, ROH, the lone pair will attack. The lone pair will attack on this R and try to remove this group. And here you got to remember that this is strictly SN2 driven. This is SN2 driven, which means we can't have any type of alcohols here. We have to have alcohols which have very simple alkyl groups. Okay. That means if you have CH3, CH2OH with concentrated H2SO4, at around 413 kelvins, we can say that ethers will be major product. This will be major product, and an alkene will be minor product. Now listen up. If you elevate the temperature any further here, and the clear distinction which you will observe, correct? Clear distinction which you will observe is around 170 degrees, correct? So if you make this as 170 degrees, which means another 30 degrees you have to add. So, right, so 443 kelvins here. In that case, alkene will be major product and ether will be minor product here. So it's always the temperature's gain. While if you have isopropyl alcohol, even if you're operating at constant, I mean with concentrated H2SO4, operating at 413 kelvins. Now, because it is at a secondary position, making an ascent to attack would be relatively difficult. Hence, you will end up getting alkene and this compound which is minor. So because this kind of an attack on the alkyl group will be difficult for SN2. So this alkene formation is major and ether formation is minor. Okay. So you strictly need to remember the temperature conditions. Do not worry too much about why that is happening. And so simple concentrated H2SO4 is highly temperature sensitive. Its oxidizing ability, its dehydrating ability, both depends on temperature. Okay. So as you go for the higher temperature, it highly favors, sorry, excuse me. It highly favors elimination. Done. So I suppose this part is clear. Now, the second important reaction in this case, right, B, B part here is about formation of esters. This is an important area in NCERT also from this topic, formation of ethers, which is Fischer esterification. Fischer esterification. Okay. So let's see what is a Fischer esterification. If you have RC double bond OOH with R dash, sorry, let me write down this here, HOR dash, that is alcohol, in the presence of concentrated H2SO4, then we will end up getting an ester RC double bond OR dash plus H2O. And if you clearly notice that the OH from the acidic side and H from the alcohol side is eventually released after the mechanism, that's how you will get an ester form. Okay, so now let's notice on the mechanism here, everybody. So if you have, the mechanism typically is done by SNTD method, okay, or also known as acid catalyzed acyl bond formation of addition type. A means addition, AC2. Now what does this mean? Let me explain point by point here. For example, if you have RC double bond OOH, the minute you push H plus into the solution, the lone pair from this oxygen will take this H plus, convert into RC double bond OH plus and OH here. You might ask, sir, why only this one? Why not alcohol is taking? Simple reason. If the H plus is been taken here, notice it carefully. It gives a equivalent resonating structure. So this with OH and double bond OH plus. Clear? You will get this as 1 and 2. These two are equivalent resonating structures. So guys, let's put this as step 1. Okay. Step 1 is generating these equivalent resonating forms. And now, because of the positive charge on oxygen here, that will induce a sufficient positive charge on carbon. And that becomes a hint for alcohol to attack. Okay, just a second. Right. See, so alcohol would attack on it. Right. So alcohol as a nucleophile will attack on this position. Now, as it attacks, the pi bond from here will shift upwards. Pi bond from here will shift upwards, and we'll end up getting this is RCOH and OH and OH and R here. Okay, R dash, R dash here. Okay, with plus charge. Now you would notice that an internal proton transfer will take place, IMPT, which means the lone pair from this oxygen will take up this H plus. In fact, you can say, sir, why not this oxygen? Well, it's the same. Whether you take this oxygen to take H plus or this oxygen to take H plus, it's the same thing because both of them are equal in quantity. So you can take this as ROH, then we have OH2 plus, and we have this as OR dash. That's when the lone pair on this oxygen will push it back because you would now realize there is a better leaving group in this case. That leaving group will make it to convert as C double bond OH plus, and then we have OR minus. So that becomes our last step, which is RC double bond O H plus and OR dash minus will give away H plus and convert into an ester. And ester is a fruity smelling, fruity smelling liquid or vapors. Okay. Typically, this is how the mechanism happens. And now you can see in this reaction, right? So see, if you have this ester form here, right? Uh, in this case, have you noticed that first an addition of alcohol has happened? It got changed from sp2 carbon to sp3 carbon. So when a mechanism changes from sp2 to sp3, which means from a planar molecule, this is planar molecule, to a tetrahedral structure, right? Then that is called as SNTD mechanism. SNTD means substitution reaction via tetrahedral formation. Alternatively, it is also called as addition elimination reaction. It has undergone addition and then elimination. Okay, so you could clearly notice that first addition has happened and then elimination has happened here. So here elimination has taken place. Got it? Which is the rate determining step here? So this one, where the alcohol goes and attacks here, that becomes the rate determining step, which means if at all we have any bulky groups here, either R dash or R, then that will hamper the rate of reaction. Correct? That will hinder the rate of reaction or retard the rate of reaction. Got it? So let me write down reactivity of these acids will be strictly dependent upon their crowding. So HCOOH will be more reactive than CH3COOH, then uh, dimethyl, I mean isopropyl kind of a group with COOH, and then we have Me thrice C COOH. This is the reactivity. And same goes with alcohols also. So in alcohols also, if you have CH3OH, that will be more reactive than ethanol, which is more reactive than isopropyl alcohol, which is more reactive than tert butyl alcohol. Okay, this is how the reactivity happens. So both of them steric factors. Steric factors is the reason why the reactivity is decreasing as the alkyl group increases. Okay, and another thing, note when I wrote the word AAC twice, which means acid catalyzed, okay, acyl addition. At acyl position, the addition has acyl breakage, sorry, acyl cleavage, with bimolecular reaction. Why bimolecular? In rate determining step, two molecules are involved. That's why it is bimolecular reaction. All right. So very important step, everybody. So this is how the esterification will take place. Clear? So see the questions here. First question is when you have CH3 interruption. See, in case if at all we are reacting with CH3 COOH and CH3OH, here this oxygen is isotopic and then reacting with acidic medium, you will get an ester CH3 COO CH3, and this isotopic hydro oxygen will be present 100%. So 100% only this product will come. While if I make a similar reaction now, if I make same reaction this time, but if the isotopic oxygen is on this carbon here, this oxygen here, in such case, you will get two types of products here. Correct? One, you would have with or without isotopic oxygen. With or without isotopic oxygen, and this would be 50-50 percentage. You can notice this going back to the mechanism here. See, while I told you that whether this OH or this OH, both of them, any one of them can take the proton from here and that can go as a leaving group, isn't it? So which means probability of removing this OH group or this OH group is 50-50 percentage. Therefore, if one of them is isotopic here, chances are 50% it might remain or 50% it might go away. That's why even if you have one more case, a similar kind, where isotopic oxygen is on the next oxygen here, like this. Okay, so that is at this oxygen, if you have, then also you'll get the same 50-50 percentage. Okay, so please quickly go through the mechanism once. If you may have noticed the rate of the reaction here, rate of reaction, then rate R will be equal to some constant into acid concentration, alcohol concentration, and also H plus concentration, because you'll also have an H plus concentration here. But this K into H plus concentration can be written as some K dash. Hence, rate can now be written as some K dash into acid concentration into alcoholic concentration. That implies order of the reaction is 2. That implies order of the reaction is 2. Got it? Which means if H plus concentration is increased, H plus concentration is increased, rate of esterification increases. If you may recall, we discussed this in kinetics, chemical kinetics, that if I take 1 molar HCl versus 1 molar H2SO4, now which one will make more stronger esterification? So therefore, rate of esterification, with HCl will be always less than rate of esterification with H2SO4, as long as we are talking about the same concentration. Clear? So whenever you have the concentration changing, that will also impact the rate here. Okay. Next, other type of examples, you notice that uh, you'll also see that we'll have esterification happening internally, and that will convert into an ester here like this. Similarly, if you have R C double bond OCl with R dash OH with pyridine, and correct, that will also convert into R C double bond O R dash plus HCl. Now this time it is irreversible. So why is it irreversible? Because pyridine is a base. So that will react with HCl, convert the HCl part into pyridinium chloride. So like a salt form. So since it's a salt form, the reverse reaction is hardly observed, because Cl minus cannot go and replace OR minus. OR minus is a weaker Lewis group. Okay. We can do this same thing with, anhydrates and esters also. So let me copy this 2 times here. So which means, in case if you have OR dash here, okay, OR double dash, then along with this we will also have one more product, which is R double dash OH plus. Just a second, somebody's at the door. Sorry. So the same thing would happen with esters also, as well as anhydrate as well. Anhydrate. So let me show you anhydrate here. So suppose if you have OC double bond OCH3. So which means one will be ester, the other form will be alcohol here. So which will be CH3COOH. The irreversible condition is the same in all 3 cases. Everyone understood how the reaction is proceeding and what is happening here? Just push it here. Now this becomes a very, very, very important method of identifying how many number of what do you say, OCH3 groups are present. or OH groups are present. Let me explain what does that mean. See, if you have to figure out polyhalo, polyhydroxy, polyhydroxy alcohols, polyhydroxy alcohols detection. How do we do that? See, R CH with OH, and we have N times with some, let's say, R here. Okay, it could be secondary alcohol, 1 degree, 3 degree, does not make much difference. And now, this, if at all I'm reacting with, let's say, an anhydride here, acidic anhydride, CH3, CO, twice O in the presence of pyridine. What do we naturally expect? We'll expect this to form RCH, OCOCH3, and this would be N times of R, N times of R here. If this is molar mass plus CH3, COOH, yeah. If you have this molar mass as M1 and here molar mass as M2, then the number of hydroxy groups present will be M2 minus M1 by 42. Why 42? Notice this carefully. We have CHOH here, that is converting into CHOC double bond OCH3. Okay. So if you notice, the molar mass of this part is actually 43 grams or 43 units, and one hydrogen is 1 unit. Okay. So basically you are removing 1 unit and replacing that with 43 units. So net increase in the molar mass is how much? Net increase in the molar mass is 42. Okay. And that's the reason why you can use this molar mass differences to figure out how much number of polyhydroxy groups are present. Typically in all carbohydrates, whether it is glucose, fructose, sucrose, all of those cases, to identify how many number of OH groups we have, we always use this technique. We always use this technique to detect the number of OH groups present. Clear, everyone? And now see the last reaction here. This is called trans-esterification. Trans-esterification. Trans-esterification is converting one ester into the other ester. For instance, if you have R, C, double bond O, O R dash plus R double dash OH, and that if you react with concentrated H2SO4, okay, this will convert into RC double bond O, OR double dash plus R dash OH, correct? So that means one ester form is converting into other ester form. This is called trans-esterification. Well, to do that, at least we should have 1:8 ratio, mole ratio. Okay, so that you have excess amount of this alcohol, which will push here to remove this RO minus. Okay, so this is called trans-esterification, everybody. So I hope all of you understood this part. Okay, so this is the first part of the chemical reactions where we have O and H bond cleavage involved. Now the next part we will learn is about C and O bond cleavage. Okay.